Now let's examine the configuration of capacitor combined in parallel to the battery. This is positive and negative terminal battery. In parallel means the capacitors are directly wired together at one plate and directly wired together at the other plate, and at that the same potential difference V is applied across the other two groups of wired together plates. Thus each capacitor has the same potential difference V, which produces charge on the capacitor. So when a potential difference V is applied across several capacitors connected in parallel, that potential difference V is applied across each capacitor. The total charge Q stored on the capacitor is the sum of charges stored on all the capacitors. So capacitors connected in parallel can be replaced with an equivalent capacitor, like the one we did in series. Let's suppose C1, C2 and C3, and now we can draw our equivalent circuit. So the equivalent capacitor has the same total charge Q and the same potential difference as the actual capacitors. For equivalent capacitance, let's start from Q is equal to CV. The charge on actual capacitor 1 the charge on capacitor 2, the charge on capacitor 3. So the total charge on the parallel combination becomes Q, and it is equal to Q1 plus Q2 plus Q3 and C1B plus C2B plus C3B, and this is the total charge, and the total equivalent capacitance is equal to Q over V. C2 plus C3. So the same result, we can use the same procedure which we did for capacitors in series. We can extend it for n number of capacitors. So C equivalent, we will use summation, and J is equal to 1 to n C J and capacitors in parallel. Capacitors in parallel. So now let's do one sample problem to understand the concept of capacitors in series and in parallel combination. So here we need to find the equivalent capacitor, charge and potential difference for two different configurations. One is series and one is parallel. So in both parts our target variables is equivalent capacitance, then charge, and then potential. So let's start from capacitance, equivalent capacitance. The equivalent capacitance for the series combination is equal to C equivalent C1 plus 1 over C2, and it becomes 1 over microfarad plus 1 over 3 microfarad, and for simplicity 1 plus 2, 1 by 2, and your C equivalent becomes 2 microfarad. Now find out the equivalent capacitance for parallel combination. We know C equivalent is equal to C1 plus C2 microfarad plus 3 microfarad. It becomes 9 microfarad. Now let's move to find out the charge on each capacitor in series. Okay. So Q in series, Q is equal capacitance into V, and it becomes 2.0 microfarad into 18 volts. The potential difference is VAB is already given here, 18 volts. And the value of the charge becomes 36 microcoulomb. So now let's calculate the charges for the parallel combination. So here charges are Q1 and Q2 are directly proportional to the capacitances C1 and C2. You can write it for parallel. Q1 is equal to C1V. It becomes 6 into 18 is equal to 108 microcoulomb. Now Q2 is equal to C2V is equal to 3 microfarad into 18 volts, and it becomes 54 microfarad. Now let's proceed towards the potential difference. The potential difference across each capacitor is inversely proportional to its capacitance in series. So V1 becomes Q over C1, 36 microcoulomb divided by 6 microfarad is equal to 6 volts. V2 becomes Q over C2, 36 microcoulomb over 3 microfarad becomes 12 volts. And for parallel combination, we know the value of the potential difference is same across the equivalent capacitor, and it will be 18 volts. So here one point to be noted is the equivalent capacitance for the series combination. Here this one is less than either the two capacitors C1 and C2, while for the parallel combination the equivalent capacitance is indeed greater than either C1 or C2. So similarly you can also guess about charges and potential for the two capacitors. Now let's move to one more sample problem which is about the previous lecture which is on different configurations. So in this problem the plates is about a parallel plate capacitor. The plates of a parallel capacitor in vacuum are 5 millimeter apart, so the distance between two plates is 5 millimeter and 2 meter square in area, the area of the plate. Potential difference of 10,000 volts or 10 kV is applied across the capacitor. Compute the capacitance, the charge on each plate, and the magnitude of the electric field in the space between them. So we are given the plate area E. We are given the plate spacing D and the potential difference VAB for the parallel plate capacitor, and we need to find out capacitance, charge and electric field. So let's start from the capacitance, and we know for the parallel plate capacitor capacitance is equal to E epsilon naught into A over D, and now you can just put the desired value. So I divide the D is 5 millimeter, I convert it into meters, and then the capacitance becomes 3.54 of because we prefer to use micro or picofarad, that's why it's converted into micro. Now the other two, let's move to the other two targets. The charge on each plate and the magnitude of the electric field in the space between them. So in order to find the charge on the capacitor, we know Q is equal to CV. Here the potential is already given. The potential is 10,000 volts. We already find out the capacitance, and then the value of charge becomes coulomb will be the value of charge. Okay, the plate at higher potential has charge of positive 35.4 microcoulomb, and the other plate has negative charge of the same magnitude minus 30, so it becomes minus 35.4 microcoulomb. Now the magnitude, the last one is the electric field. So let's find out the magnitude of the electric field. We just calculated the charge and we know epsilon naught. Newton per coulomb or volt per meter is also a unit of electric field. We can find out the electric field by using another formula. We know that V potential difference is equal to E into D, so you can use this one as well. And so you already know that here is 10 raised to power 4 volts divided by D is 5. 10 raised to power minus 3 meter, and it becomes 2.0 into 10 raised to power 6 volt per meter. So you can use this formula as well. So this I think this sample problem will clarify more about how to calculate the capacitance, electric field and the charge. So if you have any problem in this lecture, you can discuss with me tomorrow in the discussion session.